The Tupolev Tu-95, known to NATO as the Bear, begins with precise technical drawings that define its icons.
This design prioritizes extreme range and payload, enabled by the most powerful turboprop engines ever built.
The Bear's unique turboprop configuration allows it to achieve intercontinental range while maintaining high subsonic speeds.
From these detailed drawings and exploded views, we see the engineering philosophy behind the Tu-95's longevity.
This is the Tu-95 Bear, NATO's name for it. It's powered by 4 of the most powerful turboprop engines ever.
The Tu-95 Bear, one of the most iconic strategic bombers in history, has been a cornerstone of long-range aviation since the 1950s.
Production of the Tu-95 starts with high-strength aluminum alloys, primarily duralumin-type materials combining aluminum with copper.
We heat these high-grade aluminum alloys carefully to make them malleable without losing strength, and this step is
Forging aligns the metal's internal structure, creating dense, high-strength parts like wing spars that can withstand the stresses of long-range flight. Computer-controlled machining ensures precise dimensions for frames and stringers, forming the skeletal backbone that supports the two.
Stretch forming gives us the smooth, swept wing curves needed for the Tu-95's high aspect ratio wings.
Chemical milling thins specific areas of panels, reducing overall weight, vital for achieving the intercontinental range that defines this strategic bomber.
Fuselage assembly starts with setting up the main jig, a precision fixture that ensures the Tu-95's long
These stringers run the full length of the fuselage, distributing loads and providing the backbone that supports the massive wings and engines later in assembly.
Floor beams create the platform for crew stations, equipment bays, and the bomb bay, critical for the Tu-95's role as a long-range strategic platform.
Chemically milled skin panels are now riveted in place, creating the pressurized sections for the crew while maintaining the lightweight strength needed for extreme range. Joining the sections requires sub-millimeter accuracy. Any misalignment here would affect flight characteristics across the entire airframe.
Allows fathers. With the main fuselage assembled, this robust monocoque structure is ready to receive the massive wings, tail.
Wing fabrication for the Tu-95 begins with the central torsion box, a robust 3-spar design.
These ribs maintain the airfoil shape and transfer aerodynamic loads to the spars, essential for the Tu-95's 50-meter wing. Chemically milled aluminum skins are attached to create the smooth, swept surfaces groove. The 35-degree sweep delays compression.
With the wings fully fabricated, precision alignment is critical for mating to the fuselage, ensuring the high aspect.
Integral fuel tanks are formed within the wing structure, maximizing range while the reinforced sections support the heavy engine nacelles and contra-rotating propellers.
These high aspect ratio swept wings represent the engineering triumph that enables the Tu-95's legendary endurance.
Tail assembly starts with the vertical stabilizer, a large swept fin designed to provide directional stability for the Tu-95's massive.
These ribs maintain the airfoil shaped fin while transferring aerodynamic loads on
Plates. The Tu-95 features a large, all-moving horizontal stabilizer for pitch control. Its size and adjustable.
The swept vertical fin receives its outer skins next, creating a strong, lightweight structure that maintains
balanced control surfaces reduce pilot effort and flutter risk, essential for a bomber that must remain controllable during long missions with varying fuel and payload states.
With the empennage complete, these critical surfaces are ready for mating to the rear fuselage, ensuring the Tu-95.
Engine integration begins with the enormous NK-12 turboprop, the most powerful turboprop engine ever produced.
The engine mounts are designed to handle extreme torque and vibration from the contra-rotating props.
The contra-rotating propellers eliminate torque reaction and maximize thrust efficiency, a key engineering choice that gives. All critical engine systems are connected and routed through protected pathways, ensuring reliability during long durations. The cowling is shaped to minimize drag while providing adequate cooling airflow, critical for maintaining engine. With the powerful turboprop engines fully integrated, the Tu-95 takes on its characteristic profile.
Avionics installation transforms the Tu-95 from a raw airframe into a sophisticated strategic platform, beginning with the forward nose.
These inertial and celestial navigation systems provide precise positioning even without external signals.
The nose-mounted radar serves dual roles in navigation and targeting. Its installation requires sub-millimeter.
Thousands of feet of shielded cabling link all systems, from flight controls to electronic warfare, creating a resilient net. With avionics fully installed and integrated, the Tu-95 gains its intelligence and precision strike capability.
The Airborne Defense Suite detects and counters threats. Its integration ensures the Tu-95 can penetrate defended.
Weapon systems integration focuses on the Tu-95's large internal bomb bay, a 14-meter-long compartment at the aircraft's center of.
The rotary launcher is precision-mounted to allow sequential missile release while maintaining balance, critical for the Tu-95 stability.
Each station on the drum receives launch rails and ejection systems, enabling safe, sequential release of up to 6. Bomb bay doors are sealed to maintain the aircraft's clean external profile, essential for reducing radar signature and drag during strategic missions. The rotary system allows missiles to be indexed and launched one by one, a design that maximizes internal payload.
With the rotary launcher and bomb bay fully integrated, the Tu-95 becomes a true strategic missile platform.
Final painting and coating begin after all structural and systems integration, a multi-layer process that provides corrosion.
This epoxy primer creates a durable barrier against corrosion and provides excellent adhesion for subsequent top coats.
Effectiveness. The upper surface camouflage breaks up the aircraft's outline against sky and clouds, while the white belly reduces visibility from below.
Selective application of radar-absorbent coatings on key surfaces helps reduce the Tu-95's detectability.
The clear coat seals all layers and provides UV resistance, while detailed markings ensure safety and identification.
Ground. With painting and coating complete, the Tu-95 enters the final assembly phase. Minor fittings, protective cover. Ground testing begins after final assembly, a comprehensive series of static checks to verify every system before the aircraft ever leaves the hangar floor.
Non-destructive testing confirms that all rivets, bonds, and welds meet aerospace standards.
Inertial platforms are leveled and calibrated to sub-arc-second accuracy, while radar and navigation systems.
The comprehensive ground test sequence validates every system interaction: structural, hydraulic, electrical.
Flight testing marks the culmination of years of design, fabrication, and integration. Every system must prove itself.
All 4 engines stable, prop sync confirmed, systems green, tech status Tu-95 ready for first takeoff.
First flight verifies basic handling, control response, and structural integrity under real aerodynamic loads. The high stability and control tests confirm the Tu-95's forgiving handling characteristics, critical for a bomber that must remain. Successful completion of the flight test program, including stress, flutter, weapon separation, and full systems checks, clears the aircraft for acceptance and delivery.
From initial technical drawings to this moment of delivery, the Tu-95 represents enduring engineering excellence.